Hello everybody. In this video I'm going to help you be able to finish the report for our lab this week, the determination of an equilibrium constant. The first thing you're going to do is tell them how you're going to collect the data for this experiment. You're going to choose virtually, and then you're going to be presented with a series of pictures of a burette that they're going to ask you to read and enter the volume values for over here. We need to remember that when we're reading a burette, the numbers go up as you go down, and that we should always be reading from the bottom of the meniscus. So if I'm going to read this one, I know that it is a value that is greater than 2 and less than 3. That would make this graduation right here 2.1. We should be able to estimate how much between these two graduations here to get an extra digit. So when I looked at this, I entered 2.12. Remember that last digit is really just a guesstimation there. So it really doesn't matter so much what the last digit is, just that there is one there. After that, you're going to do that a few times. And then we're going to get into our calculations, starting with the determination of the initial concentrations that we had. Now, in order to be able to do this, we need to understand exactly what we did in this lab. What we did is we started off by adding a half a mole of ethanol. Sometimes the PDF calls it ethanol, sometimes it calls it C2H5O5. And a half a mole of acetic acid, or HC2H3O2, into a round bottom flask. Now, these two are going to react to produce ethyl acetate and water, but they're not just going to do it spontaneously all on their own. We're going to have to add a catalyst, and we're going to have to heat this reaction in order to get that to happen, which is a good thing. We're going to use that to our advantage. So since this isn't reacting yet, we can get the initial concentration of acetic acid that we have in our solution in a very accurate way using titration. What we'll do is we're going to pull off 1 milliliter sample. We're going to put that into an Erlenmeyer flask. We're going to add 30 mils of water. This 30 mils of water isn't going to enter into our calculations anywhere. It's just to give us enough liquid in the bottom here to get an accurate titration. We're then going to titrate it with 0.25 molar sodium hydroxide to a phenolphthalein endpoint. Now we need to go through our calculations. We can figure out the volume of sodium hydroxide added. That's going to be the final volume of sodium hydroxide, our final reading on the burette, minus our initial reading. If we look back at the report, you can see that those values are placed in here for us. That came from our answers to these picture questions up here. And this is where we're going to add the volume of sodium hydroxide. So it's going to be this number minus that number that you're going to enter in here. After we know that, we need to figure out the moles of sodium hydroxide. That's going to be the concentration of sodium hydroxide, or 0.25 molar, times the volume of sodium hydroxide that we just calculated. This should be in liters. Once we know the moles of sodium hydroxide, we can use that to figure out the moles of acetic acid. This is a pretty easy stoichiometry right here because they just have a one-to-one relationship. So the moles of sodium hydroxide are going to be equal to the moles of acetic acid. Finally, we can calculate our initial concentration of acetic acid as the moles of acetic acid divided by the volume of the sample. And the volume of the sample is that 1 mil that we withdrew. But we need to convert that to liters, so it's going to be 0.001 liters. The next thing that we're going to do is we're going to actually start the reaction. So we're going to add our catalyst in the form of 20 drops of concentrated sulfuric acid in there. And then we're going to start to reflux it. We're going to attach a condenser to the top and we're going to heat it up. It's going to boil in here. The vapor is going to rise, but it's not going to leave this condenser. Instead, it's going to be cooled and it's going to come back down. This is going to allow us to heat the mixture without losing any of our reagents or volume. Now, this is where things get just a little bit confusing sometimes for people. The problem that we have is that we can't just simply titrate this guy again after we've refluxed it. And the reason is because we added this sulfuric acid. So we need to figure out how much sodium hydroxide we're going to have to add just to neutralize the sulfuric acid, and the rest of it that we wind up adding when we titrate this is going to be due to the acetic acid. So to do that, we have this determination of a blank. So we need to prepare a blank. What we're going to do is we're going to add our 20 drops of concentrated sulfuric acid, and we're going to add 60.6 milliliters of H2O. This is because this is the total volume of ethanol and acetic acid that we initially added. We're just going to replace it with water to make a blank. We're going to withdraw that 1 milliliter from it. We're going to put it into the flask. We're going to add a little bit of water, and we're going to titrate that. This time, we don't need to calculate any concentrations or moles or anything. All we're interested in is how much volume did it take to titrate that 20 mils of concentrated sulfuric acid. So all we need is V blank, which is going to be the final reading from the burette minus the initial reading. If we go back to our report, we would have entered the concentration of acetic acid here that we found in that first step, and then here we have our new volume readings for the blank, and we can calculate the volume of the blank and enter that here. So in our next section, we're going to need to determine the final concentration of acetic acid in our reaction mixture once we've actually done the reaction. So after we're done refluxing our reaction mixture, we would turn this off, let it cool, disassemble this apparatus and get that round bottom. We'll withdraw another 1 milliliter sample. We're going to dilute that again and perform another titration on that sample there with our 0.25 molar sodium hydroxide. We'll calculate the volume of sodium hydroxide that was added as the final value minus the initial value. And here is our little caveat though. We need to do the correction for the blank volume. So our corrected volume of sodium hydroxide is going to be this volume of sodium hydroxide we just calculated minus the volume blank that we calculated in the previous step. We'll then calculate the moles of sodium hydroxide using that corrected volume. Again, this concentration is going to be 0.25. This should be in liters. We'll handle our stoichiometry. We now know that the moles of acetic acid is going to equal the moles of sodium hydroxide we just calculated. And finally, we'll calculate the final concentration of acetic acid in the solution as the moles of acetic acid divided by the volume of our sample. Again, that's going to be 0.001 liters. If we take a look back at the report, we can see that we're going to be entering that data here. So you'll have the difference between the final and the initial here. This is going to be that corrected value where we subtract the volume of the blank, and then you'll enter the final concentration of acetic acid right here. The next thing that we're asked to do is to calculate the equilibrium constant. Now, this is a little tricky for people sometimes. just because it's a little different than the way you would typically solve these problems. But it's actually, we're making it easier. We just designed the experiment in such a way that we had good information to be able to answer this problem. So this is our reaction. We have ethanol plus acetic acid is going to form ethyl acetate and water. If we do our ice table, we started off with the initial concentrations of ethanol and acetic acid. We had yet to produce any products. Every bit of ethanol that is consumed, there will be an equal amount of the acetic acid consumed because they're in a 1-to-1 ratio. And that's going to produce 1 mole of the ethyl acetate, and it's going to produce an equal amount of the water. When we do our algebra, we get the initial minus x here for the ethanol. We get the initial amount of acetic acid minus x for the acetic acid. We're going to produce x amount of the ethyl acetate and x amount of the water. But what we have is an additional piece of information. We measured the equilibrium concentration of the acetic acid directly. We know what that is. That's this final concentration of acetic acid that we had. This is going to allow us to solve for x. So x is going to equal the initial concentration of the acetic acid minus the final concentration of the acetic acid. Now once we have that, we get quite a bit of stuff. So we already know the equilibrium concentration of acetic acid, but now that we know x, that is going to be the equilibrium concentration for the ethyl acetate, and it's going to be the equilibrium concentration for the water. The only thing we still need to know is this term right here, but we did another clever thing to allow us to know what that is. We started with equal numbers of moles of the acetic acid and the ethanol. That means that the initial concentration of ethanol is the same as the initial concentration of acetic acid, which means that this term is the same as that term, and the final concentration of ethanol is equal to the final concentration of acetic acid. So now we know all the numerical values that we need to know. We know that the concentration of the ethanol, the equilibrium concentration of ethanol, is going to equal the equilibrium concentration of the acetic acid that we calculated, and we can calculate x to get these two equilibrium concentrations. At that point, we just need to plug them into the KEQ equation for this reaction. Remember, that's products over the reactants. There are no stoichiometric coefficients to raise these two, so it's a pretty simple KEQ expression. We plug them all in, and we can calculate KEQ. We know that if this value is greater than 1, meaning the numerator, the products, are larger than the reactants, the denominator, this is going to favor the products. If the KEQ is less than 1, meaning that the numerator is smaller than the denominator, so the products are less than the reactants, this reaction is going to favor the reactants. And that's pretty much it. There's a few little conceptual questions that we need to finish up at the end here. They're going to ask you what's going to happen if instead of using fairly dry reagents, we had more dilute aqueous agents to use. How do we handle that with the KEQ? The answer that they're looking for is that water must be eliminated from the equation of KEQ. This is something that we always do when we are in dilute aqueous solutions. You really have to, otherwise those values would get to be very, very large and it just wouldn't make sense. There is some more sophisticated reasoning from that has to do with like activities and pressure coefficients and stuff, but we're not going to get into that in this class. The other ones are basic Le Chatelier's principal questions. Basically, they are asking what happens if we add or remove water from the mix. And this is a pretty basic statement here. If we remove water, then that's going to shift the equilibrium more towards the right. If we add water, that will shift the equilibrium more towards the left. And that's pretty much it.